project, which is MK-UNET. MK-UNET is a segmentation model based on a UNET backbone. It is novel in this case that while having a quite a less parameters than other state-of-the-art models, it is able to beat the state-of-the-art models by a high margin. So the thing about MK unit which makes it special are its blocks. As you can see, we have a MKIR block, which is a multi-kernel inverted residual block. So it's basically a depth-wise convolution of three different kernel sizes, and these kernel sizes can be learned by the model itself. This helps the model to adapt the kernel sizes according to the segmentation dataset that we have, because different segmentation dataset might require different kernel sizes. So the model automatically finds the best possible kernel size and uses that. After that, we have the MKIRA block, which is the multi-kernel inverted residual attention block, which contains a channel attention and a spatial attention along with the MKIR block. This is usually put in the decoder steps. Then after that, we have the grouped attention gate. So the grouped attention gate helps us grasp the context from the higher layers through skip connection when the input is being decoded. So the input can be mapped and looked at by the model in a much higher spatial context. So the key contributions of the original paper were that it uh, introduced the MKIR and MKIRA block. Also, it performed tremendously well on clinic DB dataset, achieving a accuracy of 93.48%. So now let us explore our approach and contributions. So we have used a clinic DB polyp dataset with a 80-10-10 train val test split ratio. Polyp segmentation is one of the most challenging benchmarks in the original paper due to high intra-class variability in polyp shape. The baseline MK unit also achieves a test dice of 0.93 on the subdata subset, 0.9348 on this subset under our training protocol. So now let's move to our attempt. So we have a GMKDC block first. So in this is a group invariant multi-kernel depthwise convolution block. This was our attempt, but unfortunately this did not result into better accuracy. So what we had done is like we had taken a multi-kernel depthwise convolution, but of the same kernel. So the same kernel was rotated by three different angles, which is 0 degree, 90 degree, and 270 degree, so that the model could learn about the space that the spatial orientation does not matter in the case of segmentation model. So we hoped that it would learn this feature while applying this block. After that, we added a we added a CPE, which is a convolutional positional encoding. Convolution position encoding, and then we added a squeeze and excitation gate, uh, which is just a squeeze and excitation block, which is placed in the MKR block in the encoder. Then we also added a CL dice loss. So that what the CL dice loss does is it is a topology loss which penalizes soft edges and ensures that the model produces high and sharp edges. So first we ran the model we ran the complete model with all these, and we achieved a accuracy of 0.92, which was lesser than the standard accuracy of the baseline model. Then we tried to do a GMKDC only block, which is like we tried to do an ablation study by removing all the components that we think might have worsened the accuracy. And still, when we just used the GMKDC block, we achieved a test dice of 0.923, which was not good at all. After that, we finally thought that we should use a Sobel edge signal. So Sobel edge signal is a fixed kernel, in which we use a fixed kernel which captures the edges in the x and the y direction of the image respectively. So this usually helps us to enhance the borders of the segmented mask, and helps in increasing the training accuracy. Then after that, it also has a negligible parameter cost, but we do incur some cost due to the increased channel sizes that we have uh, that we have applied after that we are getting after using the Sobel signal. So after that, using just the Sobel signal, we achieved an accuracy of 0.94, an increase of 0.006 on the over the baseline, or 6%, 0.6% over the baseline. This confirms that structurally biasing the attention gates toward object boundaries will help us get the accuracy more. So even at the cost of less parameters. So after that, we have used, these are just the experiment results, and the input resolution was 352 cross 352. We have used Adam W and a cosine annealing. We have also used the multi-scale trainings and clipping at zero point 0.5. The loss was weighted BSC and weighted IAU as given by the paper. Uh, we also attempt a hybrid CL dice loss, but it was not effective. So here are the results. We have 0.93 as the base, 0.93 is the baseline. Then we have 0.94 as an improvement. Then these are our analysis that why did attempts 1 and 2 decrease accuracy. So what we basically thought is that we kept the channel, we did not increase the number of channel sizes. So we think that increasing the number of channel sizes would have might helped us in achieving a better accuracy with the group invariant kernels, but this would have led to a dramatic increase in the number of parameters, because if we use three filters for each kernel size, which is basically the same kernel rotated in certain degree, we would end up getting 3x the channel sizes, which could affect the training process and increase the parameter count exponentially. So we did not proceed with that idea. So we stopped that idea. Now we have the architecture. So you can see the architecture as this. We have the MKIR blocks, and then we have the GAG plus Sobel uh, skip connections attached to it. Then we have the comparison with reported baselines, and here you can see the number of parameters is 34, like of MK unit is 3.16 million and 3.0, 0.314 G, and the dice is 0.9348, and our MK unit is 0.38 million, which is not as comparable as the to MK unit, but it's not of a great increase also, because the first digit has not changed, and still we have achieved some accuracy over the baseline model. So that's it, and thank you.
To explain the changes we had made in the code. So the in the MK-UNET network file, the first change is here. The convolution that processes the encoder skip feature originally took F1 input channels. I changed it to F1 plus 1 because I'm going to append a Sobel H map as an extra channel. I also added groups fallback so the convolution stays valid even when F1 plus 1 isn't divisible by the group count. The next changes we had made is you can see here. I am registering the standard Sobel X and Sobel Y kernels as buffers. Buffers are not learnable, the optimizer never touches them, but they do move to the GPU automatically with the model, which is what I want. These are fixed, analytical defined edge detectors, so there's no reason to learn them. And there we had added a helper function. So in the this section, it's a forward pass. This is where everything comes together. I compute the edge map, concatenate it to x along the channel dimensions to get x augmentation, and then feed x augmentation to wx instead of just x. Everything else stays exactly the same, the gating, the sigmoid, and importantly the final output is still x times psi, not x augmentation. So the edge signal only influences how the tension weights are computed, not what gets passed. And here, this is the new helper method. It takes the encoder feature X and runs a depthwise Sobel convolution, meaning one kernel per channel independently. Then it computes the L2 magnitude of the horizontal and the vertical gradients and averages across the channels to produce a single H map. So the output is always shape B, 1 H and W, regardless of how many channels X has.